Okay, so now that we have the membrane being semi-permeable, we have the sodium-potassium pump creating sodium and potassium gradients. We have facilitated diffusions. Let's try to put it all together so that we can understand just one thing. We already did that once with the gut epithelial cells. Let's do it again, but let's put it all together in the context of a neuron. So just to remind you, we had the uniporters. They were facilitated diffusion, things moving down their concentration gradient. And we had the symport and antiport. These were coupled transporters. They could be moving something down their concentration gradient using that energy to move something up their concentration gradient, either in the same direction or in opposite directions. And we had the sodium-potassium pump that was creating sodium and potassium gradients. So when I say gradient, I want to remind you that I am talking about an electrochemical gradient. It's not just a chemical gradient. It's easy to remember that there are more sodiums outside of the cell than inside of the cell, and more potassiums inside of the cell than outside of the cell. But it also is important to remember that sodiums and potassiums are both positively charged. And so after the sodium-potassium pump has moved 3 sodiums out and 2 potassiums in, that's already created a little bit of an electrical difference. And then the potassium pump is a little bit leaky, and that those two things working together are going to create a voltage across the membrane. There are going to be more positives on the outside of the membrane than on the inside of the membrane. And so excitable membranes will have a charge to them. So it's important to think about the electrochemical gradient because when we open a sodium channel, the sodiums aren't just going down their chemical gradient, they're also going down their electrical gradient. They're positive charged ions, sodiums, moving toward the negative side of the membrane. The cytosol is more negative. But this isn't the case with potassiums. When you open a potassium channel, even though the potassiums would have a chemical gradient, there are more potassiums inside of the cell than outside of the cell, that is offset a little bit by the voltage across the membrane. There's a positive charge on the outer membrane leaflet. And so it's not as easy for those potassiums to move across that electrochemical gradient as it is for sodiums to move across that electrochemical gradient. And that's important to remember, that it's not just a chemical gradient, but also an electrical gradient. So we did talk about the actions of the sodium-potassium pump. We are going to burn 1 ATP for every 3 sodiums out and 2 potassiums in. If you haven't done so already, you're going to want to watch this video. Burn 1 ATP to pump 3 sodiums out and 2 potassiums in. That's going to create a sodium-potassium gradient across the membrane. And if you haven't already done so, look at some of the other coupled transporters that exploit gradients. We've got a couple videos on that, and we talked about that in the last video. Okay, so now I want to talk a little bit about how we can put that all together to understand something, and that would be the action potential. And so in general, neurons are going to take information coming in, neurotransmitter is going to bind to, say, an ion channel, and that might open that ion channel and make ions flow in. And if those ions flowing in, or make ions flow out. If those ions flowing in are sodiums, then that's going to create a depolarization of the membrane. Now, if the ions flowing out are potassiums or the ions flowing in are chlorides, that's going to cause a hyperpolarization. And so this is an information transfer into the dendrite of the neuron. All of the information coming into the neuron and all of these various dendrites is going to be summed across the cell body, and at the axon hillock, if the total pluses and minuses ever exceeds the threshold potential, then a different kind of channel that is not neurotransmitter gated or chemically gated, but instead electrically gated, is going to open. So now we've got the threshold potential being reached and a voltage gated sodium channel opening at the axon hillock. And that's going to cause sodium to rush in, cause a depolarization, which will cause more voltage gated sodium channels to open, which will cause a depolarization, which will cause more sodium channels to open. And so that's going to create an all or nothing situation, or an action potential, which will travel down undiminished to the end of the axon. When it gets on to the other end, at the axon terminus on the other side, there are going to be some voltage-gated calcium channels that cause the binding of vesicles to the membrane and release of neurotransmitters. Okay, so how is resting membrane potential established? That's the sodium-potassium pump. The sodium-potassium pump is going to put more sodium outside than inside, and more potassium inside than outside. And then the other part of it is that the potassium channels are kind of leaky, and so some potassiums are going to leak out, and that's going to cause an even greater positive on the outside, negative on the inside. And there are plenty of counter ions on the inside of the cell, proteins and chlorides and what have you, that are going to maintain the negative. So when those potassiums, when the sodiums get pumped out and the potassiums leak out, that's going to create, in your average neuron, a 70 millivolt differential across that membrane, giving the cell a negative 70 millivolts across the membrane. Okay, so how did we find all of this out? We used SQUID. They have something called the SQUID giant axon. This is not a giant squid axon. This is a squid giant axon. It is just big enough that we could get all of the wires and probes into it, and we could put whatever ion concentrations inside and outside we wanted to and measure voltage across that membrane. And we kept doing that until we got to physiologic levels. And so we established what the inside and outside concentrations were for squid giant axon fairly quickly, because they had these big, fat axons that were easy to probe. As electrophysiology techniques got a little bit better, we were able to even do that with mammalian neurons, and typical mammalian neurons have about a 15 to 1 sodium gradient, more sodium outside than inside, and about a 30 to 1 potassium gradient, more potassium inside the cell than outside the cell. And so you can see now how if I open a sodium channel with more sodium outside than inside, it's going to rush in. So when the neurotransmitter binds to a sodium channel, what happens is that sodium channel opens, the sodium rushes in. And if enough depolarization happens that the voltage-gated sodium channels at the axon hillock ever reach threshold, then there will be a rapid depolarization because more sodium channels open causes the inrush of sodium, which causes more sodium channels to open, which causes the inrush of sodium. And so there's going to be a rapid depolarization, and that will cause the membrane potential to go from a -70 before to approach the theoretical sodium equilibrium potential of +60. Now, you're never actually going to get there, because what will happen before that is that you'll have a repolarization due to voltage-gated potassium channels opening. Voltage-gated potassium channels open, and there's going to be an outrush of potassium from the inside of the cells. Along with that, the sodium channels get inactivated. They don't shut, they get inactivated. A little plug will plug the hole, and they won't allow any more sodium to go through. So with the sodium channels inactivated and the potassium channels open, then you get a repolarization. And that repolarization actually goes too far and undershoots the resting membrane potential, because it's moving toward the equilibrium potential for potassium. The equilibrium potential for potassium is a -90. And so it's going to undershoot that -70, moving toward -90, before those potassium channels will finally shut, and we will reestablish the resting membrane potential by the action of the sodium-potassium pump and the leakiness of the potassium channels that established it in the first place. So you're going to want to memorize which channels are open at different phases of the action potential. Okay, so selectivity is kind of interesting. I said that there were voltage-gated sodium channels and voltage-gated potassium channels. Now, voltage-gated sodium channels, the way that they work is there are these very positively charged alpha helices, and when the membrane potential depolarizes, so that there's not as much positive on the outside as there was before, these positively charged alpha helices are going to be repulsed by the positive charge on the inside of the cell, and that's going to cause the channel to open. And it's only going to open big enough for a sodium ion to go through. And so selectivity for sodium is really easy to understand. It's a little bit more difficult to understand how a potassium channel could be selective, because sodium is smaller than potassium. So if the channel is open, it seems like sodium and potassium should both be able to go through, but it all has to do with the size of the hydrated and dehydrated, or not hydrated potassium and sodium. So when you strip the water off of the potassium, it is exactly the right size to go through that selectivity filter. There are coordinating amino acid lysines inside of the selectivity filter that are going to hand off this positively charged potassium from one to another until the potassium goes through the channel. The sodium is just too small. So you're going to want to watch this video on the potassium-sodium selectivity filter. Okay, so that's all I'm going to talk about in this video, and in the third video we're going to move on to a little bit about the hows and whys of action